Welcome, my wondrous students, to Chapter 20, where I'll be introducing you to numerous oxidation and reduction reactions. After thoroughly surveying this chapter, I discovered that it introduces or covers 28 total reactions. However, 17 of them are ones that you've already learned in previous chapters. So in reality, for Chapter 20, you really only have to learn 11 new reactions, and then remember 17 others that you already should know. In my typical style, I wish to begin by sharing a personal anecdote that has absolutely nothing to do with our subject. Back when I was in college, a roommate and really good friend of mine, who's currently a professor at Florida State University, actually, cornered me in our crusty old apartment and said, "Mike, I've just heard the most amazing song ever. It's absolutely incredible!" He then went on to provide me with a lengthy introduction to this song. He told me that it was revolutionary, that it would bring silence to the earth, calm to the heavens, peace to weary souls, that it would align the planets and stars and make all nations who heard it throw their weapons to the ground for the rest of all eternity. With such an introduction, I naturally looked at my friend and said, "Okay, what's the song?" I was expecting the most amazing musical triumph I'd ever before heard. He played it on our stereo, and I was blown away. Not because it was that great of a song, but because I thought that my friend had gone certifiably insane. I looked at him closely and realized, having known him for many years, that he was being completely serious. He really believed that this song had the power to do the things that he described. The song, just so you know, is one performed by the hip-hop artist Jay-Z. It's entitled H to the Izzo. H to the Izzo, V to the Izzy. I mean, honestly, in light of the mind-blowing introduction my friend had given me, I don't think I would have been any more shocked if he had played Who Let the Dogs Out? By the end of this chapter, you should be able to do each of the following things. You should be able to know the oxidation and reduction reactions reviewed in sections 20.1 and 20.2. Know the products formed by the following reactions: sodium borohydride, lithium borohydride, and DIBAL-Hydride reductions, chromium oxidations, Baeyer-Villiger oxidation, sharpless oxidation, osmium tetroxide oxidation, cleavage of 1,2-diols, and alkenes. You should also be able to apply this knowledge to total synthesis. As I mentioned earlier, this chapter contains 28 reactions, 17 of which you've learned before. While covering this chapter, I will not be teaching you any reaction mechanisms. The reason for this is that I don't require you to know the reaction mechanisms for the 11 new reactions covered. To review the mechanisms that I do want you to know from the 17 reactions that we've already learned, I invite you to refer to my earlier lecture videos and notes. First, I wanted to remind you of something I taught you back in Chapter 4. The proper way to define reduction and oxidation. You may remember from general chemistry that a simple way to define reduction is gaining electrons. Conversely, we can define oxidation as losing electrons. An easy way to remember this is by remembering that Leo the lion says grr. That is, losing electrons is oxidation, and gaining electrons is reduction. Another way to remember it is by remembering this mnemonic: oil rig. Oxidation is losing, and reduction is gaining. Now, during my early years of organic chemistry study, I frequently saw professors refer to certain reactions as being oxidation or reduction reactions, but it wasn't really obvious to me at the time that anything was gaining or losing electrons. As a result, I gradually assembled a short list of additional ways to spot reduction reactions and oxidation reactions without, or in circumstances where it isn't obvious who's gaining or losing electrons. So here are my additional ways of being able to quickly spot reduction reactions. If you see something gaining bonds to hydrogen, losing bonds to oxygen, or losing carbon-carbon double or triple bonds, most likely that process is a reduction reaction. Conversely, if you see a reaction in which a molecule gains bonds to oxygen, loses bonds to hydrogen, or gains double or triple bonds, then we can typically define those reactions as being oxidation reactions. With that said, I'm now going to bombard you with reactions. As I prefaced earlier, I will not be covering any reaction mechanisms here because 1, I've already taught you all of the mechanisms I want you to know for the reactions in this chapter that we've already learned. And 2, because all the new reactions in this chapter have mechanisms that are more complicated than I require you to know to meet the objectives of this course. Hence, as monotonous as it may seem, I want you to obediently memorize, like automaton robots, the reactions that we'll cover in this chapter. What reactions we start with, what reagents we add, and what products they form. We'll now begin by covering the reduction reactions introduced in section 20.1. So here's a reaction that you learned back in chapter 4, alkene hydrogenation. Thus, if I take an alkene and I react it with hydrogen gas with palladium over carbon catalyst, it will add hydrogens to the alkene, converting it into an alkane. The question is this reaction an oxidation or a reduction? Well, it might not be super obvious when you look at this process that anyone has gained or lost electrons. But if you remember my additional ways of being able to spot that from the previous slide, you can see that in this process, my alkene gained bonds to hydrogen. It also lost a carbon-carbon double bond. So by two definitions, we can see that this is a reduction reaction. Here are some more reactions covered in section 20.1 that we've also learned from previous chapters. As you may remember, we can take a ketone and react it under these conditions to completely remove this oxygen and replace it with bonds to hydrogen. This reaction is called the Wolff-Kishner reduction. Is it really a reduction? Well, once again, it might not be completely obvious if anything has gained or lost electrons. But if we go by my definitions from the previous slide, we can see that in this process I have lost bonds to oxygen and gained bonds to hydrogen. Thus we can say, yes, this is a reduction. Similarly, from chapter 18, we learned that if you take an aldehyde or a ketone and treat it with sodium borohydride followed by acid quench, you can convert it to a primary alcohol. Is this an oxidation or reduction? Well, we can see that in the starting material I've got 2 bonds between this carbon and this oxygen, and I move over to a product that only has a 1 bond, a single bond between this carbon and this oxygen. I've also gained an additional bond between this oxygen and hydrogen. Thus, by those two definitions, this is indeed a reduction reaction. So here's a reduction that you've already seen in chapter 16. I take a nitrobenzene and treat it with hydrogen gas and palladium carbon, and I can convert it into aniline. Is this an oxidation or a reduction? Well, I'm beginning here with a nitrogen that's bonded to 2 oxygen atoms, and I'm converting it into a nitrogen that's bonded to 2 hydrogen atoms. Thus, I've lost bonds to oxygen and gained bonds to hydrogen. So indeed, it is a reduction reaction. This reaction is new. We can see that if we begin with this kind of compound, a disulfide, and treat it with HCl and zinc, we actually cleave the bond between these 2 sulfur atoms and replace that with a bond to hydrogen. Is it a reduction or an oxidation? Once again, we can see that this process adds bonds to hydrogen to my beginning molecule. So thus we can say yes, it is a reduction reaction. This is another reaction that we learned back in chapter 4. If I take an alkene and I treat it with bromine, I will add a single bromine atom to each of these 2 carbons. You might remember from chapter 4 that these bromine atoms always end up adding anti to each other. So the question is, once again, is this an oxidation or reduction? Well, this might not be quite as obvious as some of the others, because I'm not gaining bonds to hydrogen or losing bonds to oxygen. What am I doing then? Well, you'll see that as I go from the starting material to my product, I have lost a carbon-carbon double bond. Thus, we can say that this is a reduction reaction. Now we'll address the oxidation reactions covered in section 20.1. These first two should look familiar to you. We originally learned them back in chapter 10. If I take an aldehyde and I treat it with this dihydrogen chromate, chromic acid, I can oxidize it all the way up to a carboxylic acid. Now you heard me say the word oxidize. Is this really an oxidation? Well, what I've done is I've taken this molecule in which I've got a carbon that has 2 total bonds to oxygen, and I've converted it into a carbon that has 3 total bonds to oxygen, 2 up here and 1 down here. Is that an oxidation? Absolutely. Similarly, if I take a secondary alcohol like this and I treat it under the same conditions, I will convert it into a ketone like the one shown here. Now this reaction is a little bit new. If I take a thiol and I treat it with nitric acid, I can actually convert it to this kind of compound, a sulfonic acid. Is this reaction an oxidation or is it a reduction? Well, you'll see that I begin here with this thiol and I convert it to a sulfur that is bonded to 3 separate oxygens. You'll see that by gaining bonds to oxygen, I have indeed oxidized the sulfur. So this reaction is an oxidation. Now you may ask, are we there yet, Professor Mike? No! Be quiet, students, or I will turn this lecture around. Yes, there are more reactions to learn, but these ones are all ones that we've covered in earlier chapters. As you may remember, if I begin with an alkene treated with hydrogen gas and a palladium carbon or platinum catalyst, I add a bunch of hydrogens to this double bond, converting it to single bond alkane. Similarly, I can take an alkyne and treat it under the same conditions and once again convert it all the way down to an alkane. Is it an oxidation or reduction reaction? Once again, I'm beginning with compounds that have either a carbon-carbon double bond or a carbon-carbon triple bond, and I'm losing those double or triple bonds and going all the way to carbon-carbon single bonds. Thus, by my definition shared earlier, it is a reduction reaction. This is a reaction that we've also covered. If you take an alkyne and treat it with hydrogen gas and Lindlar catalyst, you may remember that Lindlar catalyst is actually poisoned palladium, so it's not quite as reactive as the typical palladium carbon catalyst that we use up here. If I take Lindlar catalyst hydrogen gas, react an alkyne under those conditions, I will put hydrogens onto the alkyne, reducing it to an alkene. You have to remember for this reaction that these conditions always give me a cis or Z alkene. The hydrogens always end up adding to the same face of the alkyne, thus they end up being on the same side. And here are some slight variations which are technically new, or new-ish anyway. Thus, if we take this kind of compound, this is a carbon doubly bonded to a nitrogen. You might remember from our previous chapter, this kind of compound is called an imine. I can take this imine and treat it with hydrogen gas and palladium carbon and add hydrogens to this double bond and convert it all the way to the singly bonded amine. Is that an oxidation or reduction? Well, I've lost a double bond and I've gained bonds to hydrogen, so it is indeed a reduction. Similarly, as we covered in the previous chapter, if I take this type of compound, a carbon-nitrogen triple bond, which is called a nitrile, treat it with hydrogen gas and rainy nickel, I can also add hydrogens all over that, reducing it completely to a carbon-nitrogen single bond found in this amine product. Here are some new-ish reactions as well. Aldehydes can also be reduced to primary alcohols by reacting them with hydrogen gas and rainy nickel. Similarly, a ketone can be reduced to a secondary alcohol under the same conditions. Are these reduction reactions? Absolutely. You'll see in my starting materials I've got a carbon-oxygen double bond, and in my products I've only got a carbon-oxygen single bond. Thus, this carbon has lost a net bond to oxygen. It is therefore being reduced. Similarly, if I take an acid chloride like the one shown here and treat it with hydrogen gas and partially deactivated palladium, I can interconvert it into this aldehyde product, which is once again a very useful reaction. Now, I hasten to mention that these carbonyl reduction reactions only work on aldehydes, ketones, and acid chlorides. Thus, if you try to take a carboxylic acid, or an ester, or an amide and treat it with hydrogen gas and rainy nickel or deactivated palladium, you get absolutely no reaction. These compounds are too stable to be reduced under such mild conditions. Now you may remember this reaction from chapter 6. If I take an alkyne and I react it with sodium or lithium and liquid ammonia, I can hydrogenate that alkyne, reducing it to an alkene, but do so in a way that gives me the trans or E-alkene. This is contrasted with the reduction that I get of an alkyne using Lindlar catalyst, which gives me the cis or Z-alkene. This is a cool example. If I take this compound, which has an alkene in it and an alkyne, and I treat it under these conditions, you'll see that these conditions do not reduce or touch the alkene. They only reduce the alkyne, and they do so in a way in which those two hydrogens are trans to each other. Thus, this alkene product that I get is actually E relative to the alkene that has been reduced. We'll now turn to hydride reduction reactions, which you should be familiar with at this stage, because I already covered them back in chapter 18. Bears beats Battlestar Galactica. You might ask, why in the crap are we covering these reactions again? I don't know. Just shut up and listen. As we highlighted back in chapter 18, hydride reactions, as well as most of our carbonyl reactions from previous chapters, are kind of like a football to the groin. Thus, H- or hydride comes in to this carbon, which is kind of like this crotch of my little stick figure, thrusting these electrons up onto the oxygen to give me this tetrahedral intermediate. The negatively charged oxygen then gets protonated to generate this alcohol shown here. The first reaction from our hydride reduction family is the treatment of aldehydes, ketones, or acid chlorides with sodium borohydride, followed by an acid quench. As we've already discussed in chapter 18, if you take an aldehyde, treat it with sodium borohydride, the H- comes right into that carbonyl carbon, thrusts the electrons onto the oxygen, which then gets quenched, giving me a primary alcohol. If I do the same reaction with a ketone, the H- comes up, electrons go up onto the oxygen, it gets quenched with the acid and gives me a secondary alcohol. If I take sodium borohydride and react it with an acid chloride, the H- goes up to this carbonyl carbon, electrons go up onto the oxygen, then the electrons come down and kick off the chloride. That gives me a temporary aldehyde intermediate. Unfortunately, I can't stop there. A second molecule of sodium borohydride comes in, thrusts in a second H-, pushing the electrons up onto the oxygen and then getting it protonated during the quench, reducing my acyl chloride all the way down to a primary alcohol. Also, as we already highlighted back in chapter 18, lithium aluminum hydride is a stronger reducing reagent than sodium borohydride. Sodium borohydride generally won't touch carboxylic acids or esters. Thus, we have to use lithium aluminum hydride, the big guns, which adds 2 successive H- into the carbonyl carbons of these starting materials, ultimately reducing them all the way down to primary alcohols. For a review of these reactions, please consult my chapter 18 video lecture. Lithium aluminum hydride can also be used to reduce amides, which sodium borohydride once again won't touch. Unlike carboxylic acids and esters, though, when amides are treated with lithium aluminum hydride, they get reduced down to amines. Thus, if I begin with this kind of amide and I treat it with lithium aluminum hydride followed by a water quench, I go all the way down to this amine. This amide, which is an amide in which the nitrogen has a methyl on it, gets reduced under the same conditions to this, a secondary amine. And if I take this kind of amide in which the nitrogen has 2 methyls or any other alkyl group you can think of and treat it under the same conditions, it gets reduced all the way down to this tertiary amine. Now, if you want to review any of these reactions, I invite you to go back and watch my lecture video from chapter 18. So what if I have an ester and I only want to reduce it to an aldehyde instead of going all the way to the primary alcohol. What can I do? Do I have to use some magical reagent like fairy dust or unicorn tears? No, I don't. What I do is I use this reagent. This reagent is called diisobutyl aluminum hydride, or DIBAL. DIBAL. When I stir an ester at negative 78 degrees Celsius, with DIBAL, I can selectively reduce it down to the aldehyde and stop, rather than going all the way to a primary alcohol. Now, I gotta be honest, there are 5 moments in my life that I would consider to be the most amazing experiences I've ever had. The first one is when my wife and I got married. The second, third, and fourth are when my 3 children were born. And the 5th is when I learned this reaction. Yeah, actually, I'm lying. This reaction isn't quite that exciting, but it's, still okay. And I still want you to know it. Now, because sodium borohydride is strong enough to reduce ketones and aldehydes, but too weak to touch esters or carboxylic acids, you can use sodium borohydride to selectively reduce an aldehyde or ketone group in a compound like this. You'll notice that this compound has an ester and a ketone in it. Once again, sodium borohydride will not touch the ester. It's not strong enough. But it will reduce the ketone to an alcohol. So if I have a compound like this, react with sodium borohydride followed by water or acid quench, I can get this product in which the ketone group has been reduced only and the ester has been left untouched. Now, just so you know, alkenes and alkynes do not possess a partial positive charge the way a carbonyl carbon does. Thus, if you take an alkene or an alkyne and try to reduce it with sodium borohydride, you get no reduction reaction occurring. This is also useful detail to know, just in case you have a compound that has a ketone and an alkene or an alkyne in the same compound. You can selectively reduce the ketone or aldehyde and leave the alkene and alkyne alone. We now turn back to chromium oxidation reactions, which we first covered back in Chapter 10. As you might remember, if I take a primary alcohol and treat it with this dihydrogen chromate, or chromic acid, I can oxidize it all the way up to a carboxylic acid. Now, presumably, the aldehyde intermediate does exist along the way, but it's not able to be isolated. In fact, this oxidizing reagent is so powerful that it does take the primary alcohol all the way up to the carboxylic acid. If I take a secondary alcohol, however, and treat it under the same conditions, it goes to the ketone. The reason is because I only have a single hydrogen in a secondary alcohol bound to this carbon that can be removed and replaced with an extra bond to the oxygen. In a primary alcohol, in contrast, I've got 2 hydrogens that can be removed and replaced with net gain bond to oxygen. Thus, a primary alcohol being oxidized under these conditions gives carboxylic acid, and a secondary alcohol gives a ketone. Now you might wonder, well, how in the world can I get an aldehyde if I want to? Well, once again, you may remember that if I start with a primary alcohol and treat it with PCC, which is a milder oxidizing reagent, I can go up to an aldehyde and stop. PCC only goes up 1 net bond to oxygen and stops. Now you should keep in mind, however, that secondary alcohols only have a single hydrogen, and thus, when you oxidize them with PCC, we go up 1 net bond to oxygen to form a ketone. So a secondary alcohol, when treated with PCC, gives a ketone, just like the chromic acid oxidation also gives a ketone from a secondary alcohol. Now be prepared. The reaction I'm about to teach you is absolutely revolutionary. It's apocalyptic. It's intense. It will bring kings to their knees, empires to ruin, and monkeys to clearance sales at Walmart. It is the Baeyer-Villiger oxidation. In this reaction, if I begin with an aldehyde or a ketone and treat it with a peroxy acid, what I will get is a carboxylic acid or an ester, respectively. So once again, I want you to look at that. An aldehyde treated with peroxy acid gets an oxygen inserted between the hydrogen and the carbon, giving me a carboxylic acid. Similarly, a ketone treated with a peroxy acid gets an oxygen inserted between the carbonyl carbon and one of the alkyl groups, giving me an ester. Now, I don't want you guys to confuse this reaction with the one that we learned earlier back in Chapter 4. As you might recall, if I have an alkene and I treat it with a peroxy acid, this alkene gains a bond to oxygen to convert into an epoxide. Please don't get these two reactions mixed up. Although they involve the exact same reagent, a peroxy acid, they do completely different things. Once again, Baeyer-Villiger oxidation uses peroxy acid to convert an aldehyde into a carboxylic acid or a ketone into an ester, while this epoxidation reaction takes an alkene and converts it into an epoxide using the same conditions. So you might wonder, what if I use a peroxy acid on a molecule that has both an alkene and an aldehyde or a ketone in it? Will I do an epoxidation or will I do a Baeyer-Villiger oxidation? My carefully calculated answer to that question is yes. Now let's examine using a Baeyer-Villiger oxidation with an asymmetrical ketone. Here's my ketone. I treat it with my peroxy acid. The question is, where does the oxygen go? Does the oxygen go in between the carbonyl carbon and this methyl? Or does the oxygen go between this carbonyl carbon and this cyclohexyl group? The answer to that question is simple. In general, a hydrogen atom always gets moved the easiest. So if this were an aldehyde, the oxygen will always go in between the hydrogen and the carbonyl carbon. If you've got a ketone, however, then the oxygen ends up going, in general, between the carbonyl carbon and the more substituted carbon group, according to this convoluted-looking trend, which, to be quite honest, is hard to follow unless you're a gypsy with a crystal ball or you possess the ability to derive the Schrödinger equation in your sleep. In any event, I don't require you to know this trend, but if your curiosity persists more deeply and you really want to know why this trend is the way it is, you can talk to me during or outside of class. Now, to me, this seems like a great place for us to end. Please rest, and while you're sleeping, leave all of your valuables at the following address: 3255 West New Hampton Haven at Chiquiparang Drive. I'll see you during our next lecture.